Let's see, can you hear me if I speak like this? Or no? Over here? Okay, cool. So I'm Nick Root. I'm a graduate student in V.S. Ramachandran's lab at UCSD, and I study grapheme color synesthesia. And when we describe grapheme color synesthesia, usually what we say is that a grapheme, like a letter, will automatically and consistently induce the sensation of a specific color. So there's a lot of modifier words in there. I'm going to say it again, that the perception of a grapheme, which is like a letter, will automatically induce a consistent sensation of a single color. So here are some synesthetes from our lab, and let's dial down a little bit. Here's one. And so when we say the word consistent, what we're talking about is that if I ask this synesthete what color, say, E is one day, and then I ask them even a year later, they'll often give me exactly the same answer. And this is almost how researchers define grapheme color synesthesia, right? Is by test-retest consistency. What we don't mean is that two different synesthetes will have consistent associations. Because if we look at these ones, for this synesthete, G is red. For this synesthete, G is green. And so associations between synesthetes often seem inconsistent. It seems idiosyncratic. It seems random. And so for a while, when somebody would talk about synesthesia in a classroom and the students ask the question that they always ask, which is like, why is this synesthete's G red? The answer, the received wisdom for a while was, well, it's random. Something that happened to them as a child, this or that. And I think scientists are never really that happy when they hear it's just random. And so, of course, we kept looking. And so, as many of you probably know, once you get a lot of data, things start to make a little more sense. So here is a group of about 20 synesthetes, subset of our hundreds. And I just want to draw your attention to G because we seem to be picking on it today. And so if I show you all of the colors for these synesthetes G, you'll notice that many of them seem green. I can do this a little more formally. I can take some students that don't know what's going on, and I can show them these colors, and I can say, what's the category of this color? And here's what they come up with. And now I can take this, and I can build a nice little graph like that. And hey, look, 60% of our synesthetes report that G is green. There were 11 choices, so you would expect it to be 9%, and it's 60. So here's an example where it's not random. Now here's the whole alphabet. This is probably a little too confusing to pick out anything here, so what I'm going to do is I'm just going to keep the ones that are statistically significant, and I'm going to put them down here to make it easier to see. And so here are, in our database of about 100 synesthetes, all of the statistically significant letter color associations that we see. There's 19 of them, 19 out of 26 letters. That doesn't sound very random to me, right? It didn't sound random to any of the researchers all over the world that do this research either. And so they started coming up with explanations for why you see patterns like this. So let's start with an easy one. B is blue. G is green. P is purple or pink. Wonder what could be going on here, right? That's an easy one. So it seems as if one factor that explains the data that we see here is that the first letter of a color term can influence a grapheme color synesthesia association, right? And so we're going to call this the color name explanatory factor. There are dozens of these things. Color name is one. Here's another one. It's a little bit trickier, but this comes out of some really, really elegant work from Daphne Mauer's lab in kids that don't have their letters yet. And so it turns out that even these are non-synesthetes, these are little kids, they don't know their letters, and you ask them to find a toy that's shaped like an O, or to find a toy that's shaped like an X, and you have piles of toys that are different colors. And what you show is that these kids will search for an O shape or an I shape in the white pile, and they'll search for an X or a Z in the black pile. They'll search for a C in the yellow pile. And so this is happening even though they don't know what those letters are. And so what came out of this was it seems as if shapes can also influence the colors that you and I would assign to these letters. And lo and behold, go look in synesthetes and you see the same thing. I and O are white more often than you'd expect. X and Z, black more often than you'd expect. And so we might call this a visual shape explanatory factor. So here's two. There's like a dozen at least. Semantic association, sound, letter frequency, so on and so forth. But what I want you to notice is that these two different factors make incongruent predictions about a particular letter. Because the visual shape predicts that O should be white, and the color name predicts that O should be orange, right? So they disagree. And that's perfectly fine because we can test that. So here is all of the colors that synesthetes experience for O, and here's all the colors that they experience for the whole alphabet. Same style graph as before. And now what I'm going to do is a little bit of statistics. I'm going to do a chi-squared test where I say, did this distribution come from this distribution? And when you plot the residuals of that, you end up with, I think, a much more easily interpretable graph. And so what this means is, if it's high, if it's big, it means that that particular letter is likelier than you would expect to be associated with that particular color. And so when you look at O here, you see the white, right? O is likelier to be white than you would expect. And you don't see the orange. And so, at least in this case, we can say when the shape explanatory factor and the color name explanatory factor disagree about this, the shape one seems to win, right? So this is one example. And this is, again, an example of what happens when two of these factors make incongruent predictions. What if they make congruent predictions? This is a result that has been replicated over and over and over again. It's probably the single most included sentence in any paper about synesthetic associations. A is always red, right? And so why? Well, there are as many explanations as there are papers that say this. So you'll get somebody, the classic explanation is A is red because A is for apple and apples are red. Another potential explanation is that it's because of how A sounds. So this is some of Mark's research, and some other people have done this too, showing that sounds like ah and eh tend to be reddish, and sounds like I and e tend to be more greenish. You can also say that it's something about the shape of A that is making it red. So these were people saying if you look closely, M tends to be red too. So maybe sort of upward pointy things are red. And then finally, there was a group of people that did some research with calendar synesthetes. And since January tends to be red, and since Monday tends to be red, they said maybe A is red because it's the first letter of the alphabet, that it's an ordinality thing. So here are four completely different explanations for why A is red, and they're confounded. We can't tell them apart. Well, we can't tell them apart in English. In Dutch, A is for ape, and apes are brown. In Spanish, when you want to say the sound eh, you use the letter e. In Japanese, the kana for A looks nothing like the letter A. And in Korean, G is the first letter of the alphabet. So if you had data from these languages, you could try to disentangle these different hypotheses. And so that's what we did. I started a collaboration with several synesthesia researchers around the world, Romko Rao in Amsterdam, and Helena Malero in Spain, and Michiko Asano and Katsuhiko Yokosawa in Japan, and Chaeyoung Kim in Korea. And we put all of our data together, and so now we have a multi-language synesthesia data set, and we can look at this question. So let's start with the semantic explanation. Why is A red? A is red because A is for apple and apples are red. And so what we did is we replicated the methodology that they used to sort of show that semantic associations in general can explain these pairings. And so what you do is you ask one group of subjects, give me a word that starts with A. Give me a word that starts with B. Give me a word that starts with C. And they keep doing this. And so they generate words. And then you look and see what words get commonly generated. You take those words, you give them to a different group of people, and you ask those people, what color is this word? And what you end up with are these potential words where a lot of people generate them and they have a specific color. And so when you look in English, we replicate this paper, and in fact, a huge number of people, when you ask them to generate a word that starts with A, pick apple, and English speakers agree that apples are red. In Dutch, instead you see A is for ape, and apes are brown. The word for apple also starts with A in Dutch, but actually Dutch people are split between red and green. And then in Spanish, apple is manzana, so that's not even there. A is for azul, and, well, blue is blue, right? So if the semantic hypothesis is explaining why A is red, then the Dutch A should be brown, and the Spanish A should be blue. But they're not. They're all red. So although the semantic hypothesis does seem to explain some associations, it's probably not responsible for this one. How about the sound? We're going to be really generous to the auditory hypothesis here, and we're going to say it could be a couple different things. It could be the sound of the letter, the way that we say it in the alphabet. It could be A, the A sound, or it could be the ah sound. And it turns out it doesn't matter, because in Korean, the letters that encode both of those sounds, neither of them is red. And so the auditory hypothesis, the sound hypothesis, is not consistent in all of our languages. We can look at shape too. We can look at the most visually similar shapes to A in languages that don't use the Roman alphabet, and they are also not read more than chance. And then we come to the ordinal hypothesis. And here's the kicker. In almost every language in the world, the ah sound, or the letter that's equivalent to A, is the first letter of the alphabet. In Korean, it's not. In Korean, the ga, or the g, it's like giok, is the first letter of the alphabet. So G is the first letter of the alphabet. And in Korean, G is red. A is not red. G is the only letter in Korean that's red. And so when we combine data from many languages like this, we can disentangle these hypotheses and say that probably the reason that A is red is because it's the first letter of the alphabet. This doesn't mean that these other explanatory factors are wrong all the time. They're not. They're right a lot of the time, right? They explain other letters, but they don't seem to explain A. So that's sort of the trees interpretation. And the forest interpretation, when we back up, is that when we compare data from multiple languages, we can sort of test hypotheses about what causes synesthetic association to happen. And we can ask whether the same features drive it in every language, whether there's universals, whether there's language-specific rules. So let me just give you a couple quick examples of those. So go back to the Daphne Maurer stuff, that O tends to be white and that X tends to be black. And it turns out that this is very consistent across all of the languages in our data set. So the only one it doesn't work for is Spanish. I is yellow. I don't know why. Somebody can figure that out. But I and O are white in Dutch, X and Z are black in Dutch, likewise with O, X, and Z in Spanish. And interestingly, in Korean, the two graphemes that look a lot like O and I are also white. And this is, I think, particularly interesting because this is the ng sound if it's not the initial letter, and it's the null, it's the there's no consonant here character if it's the initial. And so in no way ever does this character encode something that has the same sound as the O in other languages. It doesn't share any ordinal properties. It's not in the same place in the alphabet. And it doesn't share any semantic properties. There's no words that are white that start with this in Korean. And so, again, we can look at all these other hypotheses, look at all these other languages, and say it really seems as if every language that we have looked at thus far that has a circle shape, that circle shape is white. And so here's an example of a potentially universal rule about synesthetic associations. On the other hand, when you look through all of the different associations in different languages and you ask whether or not color name can affect associations, what you find is in English, they basically all do. In English, the color name explanatory factor is great at predicting colors. So the only exception here is, well, brown and black don't get B because B gets blue, but also O gets white instead of orange. But it's great. 9 of the 11 basic color terms influence the letter in some way that's statistically significant. However, if you look at Dutch, Spanish, and Korean, you only see 3 of 11 and 1 of 11 and 1 of 11 of the color names influencing the grapheme color associations. And if you just do some Monte Carlo simulations and you ask how likely is that to have happened by chance, it could happen all the time. Like 14% of the time you would see this result just by chance. And so we really don't have any evidence that color names affect grapheme color associations in these other languages. It seems to be an English thing. Why? We're not sure yet. I'm going to throw a speculation out there that's something that we're currently working on and that we're massaging this data to look at, which is that English is kind of a horrible language for sound. It's very, very opaque language, right? So if you want to know how to pronounce the letters O-U-G-H, it depends. There's like 30 different ways to pronounce it. And so one of the things that you see in English is that sound doesn't affect associations at all. That's been replicated a couple times. Whereas if you look in a language like Japanese, some of Michiko Asano's work, you do see an effect of sound. And so maybe these language-specific rules are latching on to the idea that certain properties are more salient in certain languages. And if you could characterize that somehow, you could explain why some rules tend to be language independent and some rules tend to only work for one language. But in conclusion, there are numerous explanatory factors. There are numerous things that explain why certain letters are certain colors, and each of them successfully describes some subset of associations in some subset of languages. And some of them appear to be language independent. They can describe successfully some subset of associations in all the languages we look at. Some of them appear to be language specific, so some subset of associations in some subset of languages, or in one language even. And in the future, let's try to explain that. But really, the conclusion that I want to leave everyone with is when you look at the literature, all but maybe 3 or 4 synesthesia papers that have been published that talk about these types of things, what causes synesthetic associations. They're all published using data from English speakers. And the few that don't, the few that use data from other languages, don't really compare what they find and don't use language as a means to explain what they find. And I think the reason for that is because to do that, you really need to have data from two languages simultaneously. That's the only way that you could do something like that. And so I just want to encourage everyone who's doing research where they want to say, here's the reason that we see this particular pattern, to ask whether that's something that they see only in one language, and whether the fact that we're all using English as our sort of language of research is restricting what we could find. And that's what I have, so thank you. Any questions? Or? Yeah.